Okay, so we'll be talking about GANs mostly. So we'll go into a little bit of basics first of the generative models, and we'll discuss a couple of generative models, and then we'll go into how GANs involved and like what are the advantages and disadvantages of GANs, and then finally we'll be looking at some of the implementations of GANs. So in a generative model, the objective is that we are given some training data and we want to learn the distribution of that training data. And once we learn the distribution, so that we can sample out new data from and generate new training data from that. So if we are given, let's say, a couple of face images, then we should be able to learn new faces. And there are two main types of generative models. One of them does an explicit density estimation, and the other one does an implicit density estimation. Okay, so just a little thing that I'd like to say out right here is that if you feel that you're getting lost at any point of time, feel free to jump in and ask any questions that you have, because we might have like a little less time at the end. So for generative models, what the explicit density estimation model tries to do is, given some training data, it tries to find out the original distribution of the training data, which is basically like fitting a model to the given data. And then once we have learned this model, then we can sample new data from this model. In contrast, the implicit density estimation model gets some training data, but it does not actually learn the training distribution, but it gives us the flexibility to generate new samples without even learning the probability distribution. And we'll see later how it does that. And GANs is an example of implicit density estimation. So why should we at all study generative modeling? Because it gives us the ability to generate new images, let's say, if you're working with images. But we have lots of images, so why do we need more images? And we could need, like, generative modeling is studied because it gives us the ability to learn probability distributions in a higher dimension. So that is one thing. It can also be incorporated in reinforcement learning algorithms, which we will talk about later. And the models that we have studied till now were that we had only like one correct output for the input. Like when we were classifying MS data, we had each particular class, like only one correct output for each particular image. But there could also be cases where we have multiple correct outputs for some input. Like for this example, if the input is that we want to generate some images of birds which has a pink breast and crown and black primaries or secondaries, so then all of these images may be perfectly good because let's say that this has a pink breast and crown and some black primaries and secondaries. There are a couple of more reasons to study generative models. One of them is where we're creating art. Like for this model, if you look closely, there's a green line here, which is drawn, and then it generates this green grass patch. And if you just make something like a mountain here, it gives you options to choose which of the images that you want. So it is like creating art. It is also useful in image-to-image translation applications where, given a sketch image, we want to generate an actual image which is colored. So generative models help in these kinds of tasks as well. And the basic, how generative models work basically is that they work where the principle of maximum likelihood, which we have heard a couple of times. It is just trying to find out which probability distribution would try to maximize the likelihood of the data. I won't go into the details of maximum likelihood, but there is some text available in the slides if you want to go over it later. So first of all, let's see how generative models are classified into different categories, and then we'll go into details of all of these models. So the work by the principle of maximum likelihood, as it said, there are two types of models: explicit density and implicit density models. For explicit density models, there are some models which can give us a complete picture of the probability distribution, and there are some other models which give us only like an approximate probability distribution. And we'll talk about some of these, like we'll talk about pixel RNNs, we'll talk about variation autoencoders, and then there are some implicit density estimation models, and GANs come under implicit density estimation. So we'll talk about GANs as well. These are the three. Sure.
Yeah, just had a question. Could you explain implicit density once again? I didn't get that.
So in implicit density, we are not actually extracting the whole probability distribution as to how the data is located, but we just want the ability to be able to sample from it without even knowing what the actual distribution looks like. So that is the intuition,
Okay.
and like that's the overall idea, and you'll see like how it works.
Got it. Okay, thank you.
So we are not interested exactly in knowing what the actual distribution is, but we need to know the idea, or we need to know how to generate a new sample that belongs to that distribution. So it's not going to give us the distribution details, but it's going to give us the new generated data that comes from that distribution.
Got it. Thank you.
So we'll talk about three models. I'm sorry, I messed up the numbers here. So we'll talk about pixel RNNs, we'll talk about variation autoencoders, and GANs finally. So as I said, explicit density models do an exact density estimation or an approximate density estimation. And there are some models which allow us that to efficiently compute that distribution, or others that make approximation. I think this is probably because of Google slides that these numbers are messed up. Okay. So let's talk about one of these networks. Let's say that we have this probability distribution that we are trying to estimate. So we can do it in a chain-wise manner, where given one of we have like this probability distribution of xi conditioned on all the previous xi, and then so this basically represents our whole probability distribution of the model that we're trying to fit. So we'll see that the drawback of this is because this is computed sequentially, and we need to find an ordering of these xi so that we can compute the distribution one after the other, and so this is computationally expensive. And GANs, because they do it in parallel, so they don't have this disadvantage. So we'll be talking about pixel RNNs, which comes under explicit density, and tractable density, which means that we'll be able to approximate it fully without any approximations. So what pixel RNNs do is, let's say that we want to generate this image. So we can start from one of the corner pixels. We can pick any value of this, and then conditioned on this pixel value, we can generate the nearby pixels, and then conditioned on these things, we can generate newer pixels, like we did using an RNN or maybe an LSTM. So because we're doing it pixel by pixel, so it's computationally expensive. And instead of RNNs, we can do it with CNNs as well, where we give the context region of the generated image till now, and we want to find out the probability distribution for this pixel as to what it could be, and then we can sample from this and like generate this pixel value and go on. So this is a little improvement over RNNs, because we need to only have a context region and we can essentially parallelize this, but the generation is still slow because we have to generate it pixel by pixel. Oh, it's the same. So just recapping what we discussed. So this can compute an explicit likelihood, and this gives us a good evaluation metric because we know the distribution now, so we can compare the estimated distribution with the original distribution. It generates good samples, like overall good samples, but it's still not state of the art. And the major drawback is that it is slow because it is generating like pixel by pixel. So let's go into variational autoencoders have uh, where we approximate the probability distribution to get a tractable bound on it so that we can approximate it a little bit easier. So let's define the probability distribution of the model that we're trying to fit as this P of X, which is P of Z and multiplied by the conditional distribution of X given Z. And this Z is your latent variables that we'll learn in the process. This can be thought of as the latent variables that we discussed for when we were discussing PCA and SVD. So, and like also in the case of movies like Netflix, we discussed where we have different dimensions, different latent factors, like whether a movie is action or whether a movie is comedy genre. So these are the latent factors. And because we need to integrate it over all possible values of Z, so this is not tractable. So we'll try to figure out some approximation of this function which is tractable. So let's go into a little bit of background. I'm sorry. Let me just get my charger for the laptop. Just a minute. I'll be back in a minute.
All right, while he's out getting his charger. So what we are doing here is that, again, remember the encoder and the decoder that we used in the machine translation. This is something very similar, but what we are doing here is that instead of mapping the inputs to a higher dimensional space, we are actually mapping them into lower dimensional space, and the latent factors become that lower dimensional space. This is going to create some loss of information, but also it will create a summary of that information. And from that summary, we are going to decode and create samples that are also in the same dimensional feature space as the inputs. This will help us generate similar samples. So you can take it from here if you're ready, Ajit.
Sure. So in autoencoders, what we try to do is, as the professor mentioned, that we try to learn a lower dimensional representation of the data, and then we try to learn these features which are able to essentially recover the original data from the input. So let's say that we have some number of neurons here. We try to find a lower dimensional representation such that we can recover this data exactly. Like this neuron should be the same as this neuron in the output layers, and we try to learn these values. So essentially what we're trying to do is figuring out some smaller dimensional representation of the data, which gives us a good representation of the original data. And these are good features. So how do we actually learn this latent representation? We can do it by training a model like in an encoder or decoder, where the encoder is going from the original X dimensions to the Z dimension, and the decoder is going from the latent Z dimension and trying to reconstruct the original input data. And these encoders and decoders could be either fully connected networks or CNNs. And we train this using an L2 loss function. So let's say that in an optimal case, when the loss becomes 0, so then our X dash is exactly matching our input data. That means this using these features, we are able to recompute or go back to the original distribution where we of the data that we had. And once we learn these, the values of the encoder and decoder networks, then we can use this to initialize another supervised model, let's say, because till now we don't have any labels. Let's say that our training data is very small, and we have only a few labels available, but we have lots of unlabeled data, which is easy to get. So we learned a good representation of the features using only unlabeled data, and then we can use this to initialize our new supervised model with this label, uh, and then we can fine tune to learn the feature representation. Akash, you have a question?
Yeah, so this diagram just looks like a general neural network classifier, right now, as in
Right.
it's just we've just named it as an encoder, but this is what generally happens in a classifier, where we always have a lower dimensional representation and then we have an output layer. So
In neural networks, you need not have a lower dimensional representation, but here we are making it a lower dimensional representation so that only the meaningful part of the data is captured. So, yeah.
Okay.
So
What you said, Akash, is correct, actually true. This is just a normal, you can assume this is just a normal classifier or a network that does classification with one hidden layer, and that hidden layer has fewer number of neurons than the number of inputs. That's basically it.
Okay, so we discussed about autoencoders, that it captures meaningful features and it can be used to initialize a supervised model. So now the question is, can we generate new images using an autoencoder? And that is where variational autoencoders comes into the picture. So the overall structure of variational autoencoder would look similar to this structure, where we have an input data, we go into some z dimensions, and then we try to reconstruct new images or form new images from those features. So you can think of this as, let's say that we're trying to generate new face images. So then let's say we have a couple some training data of face images here. Then we learn whether that face is smiling or not smiling, or whether that face belongs to like what could be the face width or height. And these are the features that are essentially learned by the Z layer. And if we try to, let's say, sample from this Z dimension, let's say that we pick some values which says that this face should be of some particular width and height and it should not be smiling. So then we should be able to generate some new face from those features. So this is the overall intuition. And we'll see, we'll go into a little bit more detail now. So this variational autoencoders will let us sample from this model to generate new data. And we had to figure out an approximation for this P of model, which we'll do using this L function. And we'll try to maximize the likelihood of this function, which would maximize the likelihood of this function. But if one of the drawback is that if we choose a weak lower bound, then the model would not essentially learn what we are trying to make it to learn. So I mentioned the drawback. And GANs have an advantage over this, that GANs in an equilibrium state, we can prove that it is trying to recover exactly the whole distribution. And compared to the previous models that were fully visible belief networks, one of them which was pixel RNN, this is more difficult to optimize, but GANs are not an improvement in this respect. So let's say that this was our latent representation and we're trying to learn or generate new images from this latent representation. I told you the intuition that we have some latent factors and we're trying to generate the new images. So we want to estimate the parameters of this decoder network, which would allow us to generate new images. And how should we train this model? we can make some approximations as to how we want to sample from this Z distribution. So let's say that we're trying to do generate new face images. So we can make an approximation that most of the faces, or not most of the faces, the distribution of each of the features of the face images would approximately follow a Gaussian curve. Like, let's say, uh, for an attribute which is like how many faces are smiling or not smiling. So we can say that it would follow a Gaussian approximation where you have some data which is smiling, some data which is not smiling, and most of the data would lie in between. And we can represent this decoder network with a neural network or a CNN network. And we're trying to basically learn this, but the overall computation of this integral is intractable over all values of C. So there's a little bit of math here, but we can maybe just go over the intuition, and you can look at the whole math yourself later in the slides. So because this is intractable for all values of Z, and the posterior density, which is Z given X, is also intractable because this P of X is intractable. So what we try to do is, in order to model this X given Z, we also try to model Z given X. So we have now two networks, which is similar to the autoencoder network that we have, and we'll try to approximate. We'll try to figure out a lower bound which we can approximate. So this encoder network is giving from going from X to Z layers, where we have some mean and some variance of latent representation. And from this Z layer, we have a decoder network which would allow us to generate new images. And this would also give us a mean and the variance of the model X given Z. So once we learn the mean and the sigma of this, we can sample from this distribution given the mean and the sigma. We're sampling from a normal distribution, the same here, and then we'll combine these two to train the overall network. So this is the log likelihood of our original model. We apply Bayes rule on it, then we multiply by this encoder that we defined right now. So then just separating these, and then this essentially turns out to be an equation of this form, which is representing a couple of things. This is representing how well we can approximate the X given that we have the latent representation, and this is approximable, or this is tractable using some reparameterization trick which is discussed in this paper if you want to take a look. The KL divergence term is basically a distance metric for two distributions. Like we have distance defined for 2 points in some space. So this KL divergence term is actually trying to represent how similar this distribution P of Z and this Q of Z given X are similar, and it is the distance between these two distributions. This term is also distance between these two distributions, and we approximated this using a Gaussian. So this term becomes tractable, and we'll approximate this third term. So don't worry if you are not able to get exactly like what is tractable and not tractable, but just try to maybe get an overall intuition as to what is happening overall. And if you look at the math later on, maybe you'll get a much better idea.
Yeah, for the math parts, let's leave it as a reading material, Ajit, because we're running out of time as well.
Sure.
But if you guys have any questions, we can discuss over Canvas or Piazza.
Sure. So these two terms are tractable now, which we can approximate, and we'll just make, because we know that the distance term is positive, so we'll just approximate this term and make it 0. So how does it work in like an end-to-end? So this is our overall L function. We neglected the third term here. We have an input data. We have an encoder network which is giving us the mean and the variance of z given x. Then we try to sample from this distribution to figure out some particular z. And using the decoder network, we find the mean and the variance of x given z. And then we sample from this distribution to generate a new image. And this is overall trying to maximize the likelihood of this whole equation. And we compute this for each mini batch, and then we backpropagate to make the network weights learn. So this is like an autoencoder, except for that we have like a mean and the variance term in between x and z's and z and x hat. And once we have learned this, then we can just sample from this distribution in z to generate new images. So depending on what we make for z, we'll get new images. So let's see. Let's say that we have MNIST data and we represented it in 2 dimensions in z. So if you vary some particular dimension, then you can see that some image is changing from 7 to 1 and 7 to 6. And it is more obvious in case of faces. So in case of faces, let's say we are representing it in 2 dimensions. So then this dimension, if you see here, the person is not smiling. But if you go down this dimension, the person is smiling more. So this dimension is essentially capturing how much the degree of the smile, and this is capturing the head pose. So,
could you, so this is an important image actually. Could you explain to them what each image is here, and then how do we pick the images as we vary the Z1 and Z2?
Sure. So let's say that we have learned this network, and now we have this decoder network. So let's say that we pick some random Z here. So because this is in 2 dimensions, so you can say that we have some particular value, let's say 1 and 2 for this Z dimension. And then we try to pass it through like a feed forward network to this, and then we generate some value of x hat, which would be, let's say, this image. And then so because it was 1 and 2, and let's say that we keep the first dimension 1 as constant, and then we vary across the second dimension, let's say making it 2, 3, 4 and 5 and so on. So this thing would change, and we would essentially be getting these images.
So these could be either generated images, or they can also be the input images.
No, these are the generated images.
Yes, but you can actually.
These could also be the input images if the network has learned to essentially replicate the input images in the output distribution, but it could be new generated images as well, because that's the whole point of generating new data.
Yes, let's continue.
So just recapping what we learned about variational autoencoders, the advantages is that we have a principled approach of learning this, and because we are learning the encoder network as well, which can be used for other supervised learning tasks. And the drawback is that because we are approximating the whole model, so the output images are not good as the previous models. And it is also seen subjectively that the samples are quite blurrier as compared to GANs. So this was the whole background, or the 2 models that we discussed, like the pixel RNNs and the variational autoencoders. So we saw some advantages and some disadvantages, and we'll see how GANs are handling that. Any questions till now? Okay, maybe not. So let's move forward with implicit density models. And there, in explicit density models, what we were trying to do is to come up with a representation of a model ourselves, and then try to fit that model to the original training distribution that we had. In implicit density models, we don't have a notion of generating a model distribution, but we just want to be need to be able to sample or generate new data. And there are a couple of methods that we can do that. Let's say that using Markov chains or just using direct methods. So by direct methods, what we mean is that we'll just use the original training data that we had. And in Markov chains, there's a process of sampling by which we create some mini batches, which is a little bit of an expensive process. And based on those mini batches, we try to learn or generate new images. So here I'm defining a Markov chain, which is not very important for learning GANs, but you can review this later if you want to. Markov chains are slow because the process of sampling generation is very slow. And GANs avoid this problem because they use the original training data itself. So just to compare GANs versus other generative models that we have, GANs generate everything in parallel as compared to pixel RNAs, which were slow. The design of the generator function has very few restrictions. By this, I was essentially comparing this to some other model, which was Boltzmann machine, which I have not discussed yet. But the only restriction on the model which we have for GANs is that the model should be differentiable. We don't need Markov chains because we use the original training data that we had. We are not approximating anything, so there's no variational bound. And they produce better samples than most of the generative models that we have right now. So let's go into details of GANs and what they're essentially doing. So they are like autoencoders, but there's no encoder network here. And the latent representation Z that we talked about would actually be a random noise here. So there are two components in a GAN. One of them is the generator, which is the which is kind of the decoder network, which is generating images starting from random noise. And there is a discriminator as well, which is also a neural network, which is trying to discriminate or classify the generated images as being real or being fake. So like, let's say this is, these are our two networks. One of them is a generator, the other one is a discriminator. When we're starting to train both of these networks, the generator initially has not, so here the objective is to generate cat images. The generator initially has not learned anything, so it will just give us a random output, and the discriminator would say that this is not a cat image. But after some iterations, let's say it is maybe able to learn a sketch of the cat, and the discriminator would still say that it is not a real looking image. But then it would improve itself over time, and it would finally learn to generate good images, which the discriminator would not be able to tell apart from real images. And
so here, yeah, what we are doing here is that the generator, to improve the generator by providing feedback, correct? So that feedback could be coming from us as the ground truth. We can say, okay, not good, not good enough, not good enough, until it becomes better and better, just like supervised learning training. Here, of course, as humans, we are lazy. We don't want to spend all that time giving the feedback. So we created a discriminator that will do that job for us. The discriminator hopefully is a good one that will understand or differentiate a real image from a generated one. So it will take that responsibility from us, and it will generate or create the feedback for the generated network. So let's continue. And eventually what's going to happen is the generator will become so good that the discriminator will still start having difficulties understanding if it is a real image or not a real image. So it is a competition of these two networks. And we are looking for an equilibrium. An equilibrium point where the generator is producing good images that the discriminator network is having a difficult time understanding. Sorry for the interruption, Ajit. The microphone is yours.
Sure. So we have this input latent representation Z as a random noise, and we'll have some network which could be some sort of a neural network which would try to generate some image, and then this discriminator network has access to two things. One of them is the generated images from the generator network, and the other one is the training images that we have originally. So, and the goal of this discriminator network is to determine whether, excuse me, to determine whether the image is coming from a fake image or a real image. And both of them are competing against each other. So that's why it is called an adversarial method, where the discriminator is trying to fool this network and saying that the generated images are fake, whereas the generator is trying to learn to generate good images so as to fool the discriminator. So it is called adversarial, but we can also think of it as being cooperative, where both of the networks are trying to give feedback to each other so that they are both learning over time. So initially, once we have not trained anything, the generator would generate some garbage image, and the discriminator would say that it's not an image. But then the generator would try to go uphill in that output and essentially learn to generate good images. So this is the overall intuition as to how the model would get trained. So this is just one more example. Let's say that this is a real image sampled from the original training data that we had, and this function D is the discriminator. So the goal of this discriminator is to be able to say that D of X would be 1, which means that this is a real image, and if it says 0, it means that it's a fake image. So basically the output of the discriminator would be in the range of 0 to 1. And let's say that this is a generated fake image, which is generated from an input random noise Z. We pass it to the generator network G, and it generates some image like this. And if once we pass on this generated image through the discriminator, the discriminator would try to say that this is a fake image because that is it is what's trying to do. But the generator wants to fool the discriminator, and the generator G is trying to make this output D of G of Z, which is the output of the discriminator for G of Z, which is the fake image, to be 1. And if this output is 1, it means that the discriminator was not able to identify that this was a fake image. Is everything clear till this point? Like, or do you have any questions? Okay.
Ajit, so what is the real usage of this one?
The real usage is that you will be able to generate new images given some images of some, let's say, given some images from training distribution, you'll be able to generate new and good looking images. That is all. And we discussed like why that might be a good thing to do, because like we discussed the usage of generative models. So yeah, that's what basically the outcome, or that's what we want, to be able to generate new images given some data.
And you've You consider your generation to be successful if you try to fool your discriminator or the
Discriminator.
differentiator, right?
Right.
You measure your accuracy.
Right. So this becomes like a game where both of these networks are competing against each other and trying to fool each other. And in, let's say that the models that we have discussed till now, in those models we had a lost landscape and we were trying to go do some gradient descent on that landscape so that we reach a global or a local optimum. So that was for all the models, but in cases of a game, the optimum point is not actually a single optimum, but it's rather represented as an equilibrium. And in this case, it is represented by a Nash equilibrium, which we'll discuss a little bit later as to what it exactly means. But let's say that in that equilibrium, what happens is that the discriminator is not able to tell apart the real images from the fake images, and the generator has learned so much that it is able to generate images which look like the original training images. So let's go about the cost. Let's discuss about the cost function for these networks. First of all, let's discuss about the cost function for the discriminator network. So let's say that we have some original data and X is sampled from that data, which is the original training distribution. And D of X would be the output of the discriminator for that sampled image. And D of G of Z would be the output of the discriminator for the fake generated image from the random noise Z. And this is the loss of the discriminator network, where if you are trying to minimize the loss of the discriminator, it means that this term should be close to 1, so that log of 1 is 0. And this whole term should be close to 1, which means that D of G of Z should be close to 1, which means that the discriminator was able to identify that G of Z was a fake image. So essentially, if this loss is minimized, the discriminator has learned to discriminate between the real and the fake images. All right. So this is the discriminator loss. Let's talk about the generator loss as well. But before that, there's just one point that it is shown that what the GANs are actually trying to learn is this ratio of the probability of X belonging to the data, which is the original training data, and the model that it is implicitly learning. And using this estimate, it is able to figure out, or it is able to train both of these networks. And this is like one of the things which is believed to be making GANs superior to other models. So we haven't discussed about the cost function for the generator, and because this is a game, the simplest version of the game is a zero-sum game where if one player is losing, then the other player is winning. So if we make it like a zero-sum game, then the sum of all the players' cost should be 0. So the generator's loss function would be the negative of the discriminator's loss function. And zero-sum game are also called min-max games, which is just another way to say that this is a zero-sum game. And if you notice J of D, which is this equation, then G does not ever have access to the training data X, and so there's no way that it can actually overfit to that data, because what it has access to is only the discriminator's output of the original data and the discriminator's output for the fake data, but it never gets access to the original training data. And this will be, I'll show how this is actually seen in while training GANs, but this is just an overview. And we'll train both of these networks simultaneously. So both of them do not actually have a good idea of what to do initially, but they both learn over time, giving feedback to each other. So this is the same equation from previous slide. This equation where we have removed the constants from there, and the discriminator is trying to maximize this objective now, so that this, because all of these are probability numbers, they'll both be lesser than 1, and so log would be negative, and the discriminator is trying to maximize this so that this is close to 1 and this is close to 0, whereas the generator is trying to minimize this because it is the negative of the its loss function is basically the negative of the discriminator's loss function, so it is trying to minimize this. I mentioned that to minimize or maximize this, what the values of these things should be. So how do we maximize or minimize this whole objective function? So because we have to maximize this objective function with respect to the parameters of the discriminator, so we do a gradient ascent on this discriminator because we have to maximize this. So basically what we have to do is maximize over the theta d, this whole equation, which is the same equation. And because we are minimizing this with respect to the generator parameters, so we are minimizing with respect to theta g, and only this term, the second term is dependent on theta g, the first term is only dependent on theta d, which are the parameters of the discriminator network. So any questions till now? Like, is this equation clear to you all? Or any questions on this? No? Okay, so I'll move on. But there is actually a problem with this equation. In practice, the generator objective does not do very well. This generator objective does not do very well. And why it does not do very well? Because if we look at the plot for this equation, then it looks like this. And in the x-axis, we have this term d of g of z. So if d of g of z is high, which means that the discriminator output for the generated image, fake image, is close to 1, which means that the generator is doing a good job of generating images which look like real images. But when it is already doing a good job, then the gradient value is very high. But when it is doing a bad job, when d of g of z is close to 0, then the gradient is relatively flat, and it does not get a very good feedback so that it can learn to improve more, because it is doing bad at this point. So it should be learning more at this point and less at this point. So we flip this curve a little bit so that we achieve what we are trying to achieve. So we change the objective function for the generator, and this green curve is the plot for log of d of g of z, which is achieving what we want. If the d of g of z value is close to 0, which means that the generator is not doing a good job, then it is getting a good enough gradient to learn. And if it is already doing a good job, then it does not really need to learn much, and so the gradient is relatively flat here. So we changed our objective function of the gradient of generator. Initially, we were doing a gradient descent on the generator on this objective function, but now we are doing a gradient ascent on generator, and we're trying to maximize this objective so that d of g of z would be close to 1, because that is what the generator is trying to achieve. And for the discriminator, the objective function remains the same. So now both of them are trying to maximize something, some objective function with respect to their own parameters. And this we'll try alternating between training the discriminator a little bit, and then we'll train the generator a little bit, and then we'll alternate between these two. Yeah, so both of them are trying to minimize or maximize their own objective, but they only have control over their own parameters. But the loss function, as you can see, is dependent on the other one as well. So in this case, this is described as a game rather than an optimization problem, as we have seen in previous optimization, like maybe some sort of supervised learning objective, where we have a loss landscape and we're trying to reach the global minimum. So the solution to optimization problems is a local minimum, but the solution to a game is described as a Nash equilibrium. And a Nash equilibrium is basically the values of these two theta parameters, where the loss of the discriminator is minimum with respect to its own parameters, and the loss of the generator is minimum with respect to its own parameters. So you can think of this like a saddle point, maybe, where both of a saddle point is basically minimum with respect to x and y's. So let's go into how we actually train both of these networks. So we do this for some number of iterations. We train the discriminator first for a little bit, and then we'll train the generator. We train the discriminator first because the discriminator should be able to learn something to say that this is a real or a fake image. And then we can test how much it has learned on the generator. And so we train the discriminator for some case steps. This case typically 1. And there's no real consensus. Some people believe that maybe k equal to 2 works better, but you can just take k equal to 1 for the time being. So we sample some fake images from the generator without training it. We have not trained the generator till now. We just give some random noise input to the generator. It generates some images. And then we also sample a mini batch of some real images from our original training data. And then we pass both of these real and the fake images to the discriminator so that it learns something. And because it was maximizing some objective of its own, so we learn the discriminator by a gradient ascent and trying to maximize the objective function for the discriminator. And once the discriminator has learned something, then we try to learn the generator a little bit. And so we just generate some fake images from the generator, pass it to the discriminator, and update the weights for the generator network. So this goes on for a little while until both of them learn something and reach an equilibrium. So one question here is, how do we know when should we stop training? So would anyone of you like to answer this? Okay, so I'll answer this. So when should we stop training? That when both of them have learned something and they have reached an equilibrium, as like training the generator for more iterations would not lead to anything better, and training the discriminator would also not lead to anything better, because the discriminator would now be just telling or giving a half probability to the real images as well as the fake images. And you'll see that when we are reaching the equilibrium, the losses for both of these will stabilize. And one implementation detail that you can look at while training is because the discriminator's output would be 0.5 for both of the real and the fake images, this is a good reference number for the loss point, for the loss value. So if you see that your loss is very high or very low, then you know that you're doing something wrong, and the equilibrium has not been reached yet. So let's see in a one-dimensional example as to what is actually happening. So these black dots are the original training data that we have, let's say in 1 dimension. So this is the distribution of X, where we have more points clustered in this region. And let's say that this is the current model that we have gotten till now. And this purple line is actually the ratio of these two distributions. So as I mentioned at one point, that GAN is trying to learn a ratio of the probability of the original data as compared to the probability of the model that we have. So this line is representing that. And for the generator or the model to learn something, we should be going in a direction which is increasing this towards which this purple line is increasing. So let's say at this particular point, this is the value of the on the purple curve. So it is increasing in this direction. So we should go towards the left to learn more like the data representation. So you can think like if this green curve moves to a little left, then it would closely match the data, original data distribution. So this is how the training goes as far as one dimensions is concerned. Let's say that initially the discriminator has not learned very much and it is just giving some random random outputs. This is the generator. It has not learned very much. After the discriminator, after training the discriminator for a little bit, it will stabilize its output like this. And once we train the generator a little more, it tries to closely align itself with the original training data distribution. And finally at equilibrium, the green curve, which is the generated image curve, closely matches our training distribution, original distribution. And this line is essentially representing a half because I mean, it is not right now sure as to which one belongs to the generated one or the fake ones. So this is the equilibrium position. So let's look at some results on MNIST data on which this was originally trained on in 2014. So these are some generated images which are generated from completely random noise. So these are some images which have of different classes. So if you start with different random noises, then you'll get different generated images. And these look pretty much similar to the original training data that we had. So another question is that why don't we just memorize input data and output a random image when we have to generate a new image? Because in that case, we will not have any new data. We'll just be spitting out the original data that we had. And how do we actually ensure that the model is not memorizing it? So I mentioned at one point that the generator does not actually have access to the training data. So how do we know from the results that it is not actually memorizing the data? We can look at the nearest neighbors of the images that we have generated. So the images in this inside this yellow box represent the closest nearest neighbor for each of these images. So if maybe you look at this image, this line is a little bit straight, whereas this is a little bit curved. So we figure out that this is actually a generated image and it is not being copied from our original data that we had. And so this proves that the model is really learning something and not memorizing the data. So these are some generated images again from random noise, and you can see that these are pretty good looking images which have been generated. If you just say that I want some images of churches outdoors, so then it generates some images like these, or maybe some kitchen or dining room images. And I mean, if you look in more details, then you'll figure out that these actually do not exist in the trained data, and this is like a new image which has been generated. So any questions till now?
Yeah, Ajit, I have a question.
Okay.
So like when we say random initialization, is like it can take a lot of time for the model to converge, right? So are there any practices where we give like a reference, like maybe a starting point to the generator instead of the random initialization?
No, so the generator has to learn a transformation from a noise vector to the training data distribution. So there's no, I mean, if you're talking about initial weights for the generator, then you probably cannot do that because because it is learned based on the feedback of the discriminator. So your discriminator has to learn something to give feedback to the generator, and so there's no initialization as such that you can give, I think.
Okay, thank you.
Okay, so let's move forward. So I've described a basic GAN till now, and this was introduced in 2014. And then after that, uh, a couple of people have tried to, like lots of people have tried to improve on the original structure with using like different different loss functions. Like this one is using a least squares loss function, and it is called LSGAN. And there are a lot more variations of GANs available. Collectively, they are called the GAN zoo. And we'll discuss just a couple of these GAN models. One of them is, you can look at this link to figure out, like there are thousands of GANs available. So you can look at this link maybe to figure out later, like to explore maybe. So in a convolutional GAN, instead of having neural network layers, like fully connected layers here, we have convolutional layers. And we learn to upsample from a random noise of, let's say, 100 dimensions to a 64 by 64 RGB image. And then there would also be a discriminator which is judging whether this looks like a real image or not. So for training convolutional GANs, there are a couple of guidelines that we should be using batch normalization. We should not have fully connected layers because it increases the number of parameters by a lot. And these are some activation functions that you should be using while using DC GANs, which is like the convolutional GANs. So earlier we were generating images randomly, like you just give it some random noise and it generates some images. But what if we wanted images of some particular class, like the class 0 or 1 or something? So this can be done by using something which is called a conditional GAN. So along with the random noise vector, we need to give it some additional information which says that you need to generate images of this particular class. Yeah, so that's like an example of conditional GAN. And we'll maybe see an example of a conditional GAN where we do a text to image synthesis, where we say that given this caption, this flower has some small round violet petals with purple center, generate an image which matches this description. So along with this noise vector, which is represented by a white cube here, we try to figure out an embedding of this caption, and we concatenate this with the random noise, and then we use a CNN upsampling network to generate an image. And there is a discriminator network which judges whether this generated image is real or fake. So this is about conditional GAN. There is also a concept called cycle GANs, where we can learn to transform images from one training distribution to other training distributions. Like we can convert horses to zebras and back, or apples to oranges, and so on. So these are some useful applications of GANs. So I'll just finish it up and we'll move on to hands-on maybe. So the recap of GANs is that it works without learning an explicit density function, but and it learns to generate new images from the training distribution through a minimax scheme. The pros is that the images generated are really state of the art, and maybe I can show this. So this is an image generated from random noise, and this person does not actually exist. It gives a little bit of details here. Okay, and but the major con of GANs is that it is very unstable to train, and it does not reach an equilibrium that easily. And so that's an active area of research as to figuring out uh, and trying out different losses to stabilize the training. So a recap of the whole module that we covered pixel RNNs, which use an explicit density model and they optimize an exact likelihood. The samples are good, but it's slow. For Bayesian autoencoders, they optimize an approximate likelihood, and but they have like a useful representation in the dimension z, which can be used for other tasks like initializing some supervised model. But the sample quality is blurrier, and GANs take a game theoretic approach, but it is unsafe and they generate state-of-the-art samples. But the major con is that it is unstable to train. And this has actually been improved in recent years by using different losses like Wasserstein and different types of GANs, like Wasserstein GAN is one famous example. But because they're not learning any sort of latent representation, though, so we cannot use this to initialize any other sort of models. So let's go on to the basic implementations. We'll discuss like one in detail and maybe two in just an overview. So let me start sharing again. So this is for GANs. Oh, I'm sorry, is there a question in the chat? No. So I am doing this on a GPU, and you'll probably need a GPU as well to train GANs because training on CPU will be very slow. So if you're not aware of it, I mean, you won't have access to Data Hub on UCSD, but you can use Google Colab for training on GPUs. So this allows you to run Jupyter notebooks on GPUs. So you can check this out later and run your code on this. So we're just importing a couple of functions. Verify that you have TensorFlow version 2 to run this particular code. So here we're just importing matplotlib, numpy, and keras layers. We are still working on the MNIST data. We're trying to generate new images from the MNIST data as seen in the original paper. We normalize the images to as zero mean and being in the range of -1 to 1. Originally they were in 0 to 255, and we are just normalizing it to -1 to 1. We define some configs like the batch size and the number of epochs that we want to train it for, and the number of noise, like the dimension of the noise vector that we'll give the model. And then we have like a 28 by 28 images, and this is just to generate some new images. So there's this TF data set which allows you to make your data into batches, and so that you can create mini batches and shuffle them randomly. So let's talk about the generator network that we had. So I'm defining a sequential model, which just means that I'll have a couple of layers that I can add to this model. So in the original image, I have a 28 by 28 image, which I'll reshape to being as a 784 dimensional feature vector by just flattening it. And then I'm having a fully connected layer of 256 neurons here. Then I add a batch normalization layer after it, and then I'm using a leaky ReLU activation. You can use probably a ReLU activation when you're using CNN, and you can have maybe a 5-layer conf network to this. So this is just one layer. I have another layer which is upsampling to 512 neurons now. Another batch norm and an activation layer, and another layer which is still upsampling to 1000 dimensions, a batch norm and ReLU. And finally, I have this 784 dimensional feature vector, which I'll be converting back to a 28 by 28 image. So this is my final layer of the model. And I define the forward function, and in Keras model, you need to specify whether you are in the training mode or just in the testing mode. So in the training mode, it tries to accumulate the gradients so that it can be back propagated. And in the testing mode, if you say that training is equal to false, then it would not try to compute or remember the gradients that it has collected. So I have a 3-layer generator, fully, like I have dense layers of 3 layers as my generator. And in the discriminator also, I have the same thing. I give an input to this as being a 28 by 28 image, which I have flattened. And there's a dense layer, then a leaky ReLU and a dropout to regularize. Then another layer with some dropout and another layer with some other dropout. And finally, I'm flattening it. And because I only want one output from this, like a probability of the image being real or fake. So this, the final layer is just one neuron which gives me the probability of the image being real or fake. And again, we have the same forward function for this. So we create objects of the generator and the discriminator. And then we just see how the generated image looks like if we have not trained it yet. So I create a mini batch of 4 cross 128 noise vector. I pass it on to the generator, specifying that there's no need to training as false, that I just need the generated images. And if you see, this is what the generated image looks like without training the GAN, without training the generator right now. So we'll train it using a cross entropy loss function, which I've defined here. And what should the so this is the discriminator objective. So what the discriminator should do is, for the real images, what the output should be ones. So this says that all the output should be ones. And for the fake images, so this is the output from the fake images, and these outputs should all be zeros. So this is the total loss for the discriminator, the sum of these two losses. For the generator, there's only one loss, which says that the output for the discriminator for the fake images, which is this, should be ones. So if the output is 1, which means that the generator thinks that this is actually a real image. So we define the optimizers. We are using the Adam optimizer with this learning rate for both the generator and the discriminator. So we define the training step function. This is basically running one epoch or one iteration. So we have some random noise. So this is the way that we tell TensorFlow to actually remember the gradients that are actually being computed inside this, and it remembers all the computation that you're doing inside the forward function of these, so that the gradients are back propagated later. And so I just use two gradient tapes for the discriminator and the generator. I generate some random images from fake images from starting from the noise. I pass on the noise to the generator and say that the training mode is now true. So it gives me some generated images now. And I also sample some real images from the training data, which has been passed on to this function. So the discriminator gives me the output for real images as well as for fake images. So I have the real output, I have the fake output. I compute the losses for the generator and the discriminator, and then I tell the TensorFlow that I want the gradient for these losses. So it computes the gradient of the generator loss with respect to the generator's trainable variables. So you can get the trainable variables for the generator model using this, like dot trainable variables. So it gives me the variables, and it computes the gradient of those variables with respect to the losses. So I compute the gradient for the generator, I compute the gradient for the discriminator, and then I use their optimizers to apply those gradients so that it is moving in a gradient ascent or a gradient descent fashion, depending on what the objective function is. So this is just taking one step in the direction of the gradient.
So Ajit, I have a question then. So
Okay.
we have set of images here, right?
Right.
And where are we telling the discriminator that this is a fake image or it's
right? So this is where we are telling. So let's say that this is the output for the real images, which the discriminator has outputted.
Got it.
And this is the output for the fake images, which the discriminator has outputted. So we are saying with respect to this loss that the real output should be close to 1 and the fake output should be close to 0. Right. So this is the overall objective of the discriminator, so that it is able to classify the real images as being real and the fake images as being fake. So this is where we are telling the discriminator that, hey, these are the images which are supposed to be real and these are the images which are supposed to be fake. So
let's go back to your lower cell where you have one majority. Yeah. So now this training, so in every training step you pass in the same set of images.
No, so this would be some random sample which you will see in the next step. So so we're defining this overall training function which gets the overall data set and the number of epochs that we're trying to train it for. So we do this for all epochs. We sample some image batch from the data set, which is done using tf.data.dataset, which is giving me a randomly shuffled image batch. And then I just reshape all of the images as being a single dimensional 784 feature vector, and then I pass on this image batch to the training step. So these are my real images from the training data set, and I have generated some fake images using this noise and the generator here. So now I have two things. I have a batch of real images and I have a batch of fake images, which I can then use to pass on to the discriminator, and it gives me some output for the real images. These are the real images and these are the fake images. It gives me the output for both of these, and I then compute the losses for the generator and the discriminator, and then I just move in the direction of the gradient. Is that clear now?
Yeah, so just a quick one more question. How many images are you feeding in at a given time in this training step?
How many what?
So the input of train step images, right?
This input here?
Yeah. So this is a batch. How many images are we passing in?
So that depends. That is a batch size. I'm using a batch size of 32. So in one step, I'm giving 32 images to the training.
And the generator generates 32 images as well.
Yes. So the generator would figure out like what is the batch size. I'm giving a noise vector of batch size cross noise dimensions. So for each of this noise dimension, it generates one image. So it will generate batch size number of images, which is 32. So it generates 32 fake images and 32 real images, and then we give both of them to the discriminator and we learn from there. So then I just train this model. Each epoch is taking around 1 minute. I train it for 50 epochs. And then we again see like what is the generated images based on if we give it some random noise, what does the generated images look like. So these are the generated images after training for 50 epochs. So these start to look like real images. They are not completely real. Maybe this looks like a 0, this looks like a 4 or 9 something. But you can see that the model has actually learned something, and it is generating quite realistic images. So we can maybe use CNN networks to generate better images, or train for more epochs to get really good outputs. So this was all about MNIST-GAN. If you have any questions, just feel free to ask. Maybe we can just go over another model quickly. If you have any questions, just shoot. Okay, no questions.
Ajit, you will
Sure.
upload this code to
Yeah.
GitHub, or is it already
Yes,
in GitHub?
I'll upload this to GitHub right now.
Okay.
You can run these later on, like using Colab, or if you have access to a GPU on your laptop, you can run this on your laptop as well. So let's talk about conditional GANs, where we are trying to generate images given a caption. So this is pretty much the same from previous. We'll be using a BIRDS data set, which you can download from here if you want to try it yourself. This cell is actually just for extracting the data from this data set that we have. So essentially what I'm doing is, in this data set there are two things. One of them is the image, and there's a caption associated with each image. So I'm just extracting the image, converting it to RGB, and normalizing it to -1 to 1. So just a couple of pre-processing steps here. And then I'll use I'll store them in batches, and then I'll use it to pass this images and the captions to our model to learn. So you can run these cells once, so that you don't have to generate the pre-processed data again and again, and you can save this as a pickle file, which I've done. And then again, we are using dataset to create many batches. Then I'm just seeing what the stored data looks like. So this is what the actual data looks like. This is an image of a flower. We have some conditional GAN parameters, the noise dimension, the embedding for the caption, and how many features that we want for generator and discriminator. We'll just go over the architecture of generator and discriminator quickly. We again define a sequential keras model. We have a dense layer, a batch norm, a ReLU. This is for projecting the original caption in some dimensions. For the actual generator network, what we have is, starting from random noise, we have a conv2d transpose, which is essentially upsampling from a smaller representation to a bigger representation. And you can specify the number of feature maps that you want, which is the number of filters, the input shape, the kernel size, the initializers, the strides, the padding, the data format, which I told you about earlier, which is channels first or channels last, depending on how you have stored your data. So just a couple of conv upsampling layers: batch norm, ReLU, conv, batch norm, ReLU, conv, batch norm, ReLU. So I have like a 5-layer conv network here. So I just concatenate the noise with the caption, and I pass it on to the generator to generate some images. For the discriminator, we have the same thing. We are getting an input image, and we want to classify whether it is real or fake. So we have a couple of conv, batch norm, and ReL activation layers. It is better to use leaky ReLU for discriminator, so I'm using leaky ReLU. So you have a couple of conv, batch norm, ReLU, conv, batch norm, ReLU, conv, batch norm, ReLU. So a 5-layer network here, which finally gives me an output between 0 to 1. So I have a sigmoid at the end, which says that whether this is a real image or a fake image. So I'm just concatenating the captions along with the generated image, so that it learns whether the generated image actually corresponds to the caption or not. You can look at this code later to see what is happening, but the basic architecture is we have 5 layers for the generator and 5 layers for the discriminator. I'm doing the same thing, just defining the models, the optimizers. This beta 1 and beta 2 are the momentum values. The criterion is still cross entropy loss. Label smoothing you can ignore for now. but it essentially makes the label as being 0.9 rather than 1. And this is a thing which helps in stabilizing the network. The discriminator loss is kind of the same here. For real images, we should be having the output as 1. For fake images, we should be having the output as 0. And there's a third term here which corresponds to saying whether the generated image corresponds to the caption provided or not. So this is the discriminator loss. For generator, the loss is the same, where the generator wants the output for the fake images to be ones, so that the discriminator is not able to identify it. And this is just a function for generating the image once you have trained your model. This is the same training function where we generate some images using some random noise, and then we use a discriminator to see what are the outputs. We compute the discriminator loss. So we train the discriminator once, and then we apply the gradients in the discriminator to train it, and then we train the generator some number of times. This can be one or more depending on what you want. So doing the same thing, we have some generated images using noise. We pass it through a discriminator, we compute the loss, and then we just update the optimizer and by applying the gradients. So this is like the main training code where we run it for 1000 epochs. So in the training data set, we get a batch. We pass on this batch and we create a random noise vector. We pass on all these values to the training step. The real images, the fake images, the real captions, the fake captions, the noise vector. So it trains for some time, and then we generate an output after each epoch to see how the output is looking like. So this takes around 1 minute as well for each of the epochs, and I've run it for 1000 epochs, so or maybe 500 epochs, I think. So like depending on how much you can see, like when the losses tend to stabilize, it's like 0.67 or something. So you'll see like when it is trying to stabilize. There are a couple of things that you can try to increase stability when you're doing it yourself: label smoothing, incorporate some different type of losses, and finally we just test it on the test data set. So we load the generated models after 450 epochs, and given this input caption, which is not represented as a whole. So this input caption is the flower is white and purple in color with petals that are oval shaped. So this is the generated image for this particular caption, so which looks like a flower, and it has some like white, and it is trying to incorporate maybe some purple. So these are some more generated images. So we can see that the model essentially learns how to represent petals and how to essentially attribute colors to all these. Some of the images do not look very good as well, so it's not that it has learned perfectly, but you can see that the overall general idea that it has learned something. There is also